Okay, so good evening and good morning. So I put up here a summary of various statements I made last time. So let me now kind of organize them in hopefully a coherent way. So let me just go through this quickly. So on the right are a certain set of statements about a quantum phase of matter we're going to study. And what's different here, unlike all the phases we've studied so far, this is a phase of matter that has what's called super selection sectors. I think that's the most general way to think about it. And the idea is that if you take some large region of the sample, which is part of an even larger infinite sample, then in that large region, you can define all kinds of local operators that are allowed to you. And these are operators that anything that's in the Hamiltonian is a permissible local operator that acts on the Hilbert space of states you're working with. And these local operators have the feature that they can take you out of a given sector. So the systems seem to split apart into sectors that are disconnected from each other, at least by local operators. To go from one sector to another sector, you need an operator that's highly non-local. Okay, this didn't happen in any of the problems we've studied so far, but it happens here and many other interesting phases that we're going to study. Okay, so and in some sense, the idea of quantum error correction is very much related to this, because then since no local operator can take you between sectors, if you hide your interesting quantum information in the relative phases of these sectors, you manage to create such a state, then that will be protected from any local noise. Okay, so that's the basic idea first proposed by Kiteb, how you could use this, the existence of these super selection sectors or anyons to do quantum computing. And of course, that's a big dream today, but we'll see. All right, so the simplest example we are studying has the following structure. It has 4 sectors, which are conventionally called 1, E, M, and epsilon. And these have certain topological properties. So in this particular example, these you can ask what happens when you take some region of, you imagine you have 2 very well-separated regions, each in a different sector, and you take one around the other very slowly by some adiabatic evolution. So in that process, you pick up some phase factors. In this case, they're just phase factors. Sometimes they can be matrices, and then you get non-abelian statistics. But here you only just get phases. So, and in fact, the phases are relatively simple. So these 1, E, and M sectors act like bosons, so you don't pick up anything. And the epsilon sector acts like a fermion. That means if you take an epsilon around another epsilon, you pick up a -1. One important point here, of course, is when you're talking about sectors, you don't take a sector all the way around. So if these are 2 identical sectors, you only take it halfway around, because then you can smoothly bring them back to the same original configuration, and that's an exchange. But when you have 2 distinct sectors, like any pair of these, E and epsilon, then you do have to take it all the way around. Okay, so what happens here in this case is that if you take an E all the way around an epsilon, you pick up a -1. And that's sometimes called a mutual semyon. All right, so those are the essential topological properties of this particular phase of matter. These properties, as I'll show you, were discovered in a very pedestrian way, where you just start from an actual model and you try to solve it and try to figure out what's going on at low energies. But since then, there's been an amazing set of developments in mathematics and physics where people can derive these sort of rules from almost pure thought, just by certain general constraints on what these phases can be, and the properties of topological properties of field theories. You can come up with these constraints, and this is just the simplest one of them. There's a pretty rich set of these, which I will not talk about. But these are exact results you can obtain by some very sort of general arguments. In addition, there's also the very interesting question of what happens when you have symmetries. So the models we're studying here also have symmetries. In particular, they have translational symmetry. And I'll restrict ourselves today anyway to models that also have a global U1 symmetry. Now, you could look at models that don't have these symmetries, then you can just forget about this part. And that's kind of what became clear a bit later, especially with Kitev's toric code. The toric code is a model where it has no symmetry. You can put it on any lattice with no symmetry whatsoever, but it still has these properties. However, in this matter, we invariably model the symmetry is very important. And then it turns out that you put symmetry together with super selection sectors, there are a lot of constraints. You can't just do whatever you want. There are some constraints, and I've just labeled 2 of them. And again, here there's a rich set of possibilities. And one of the things you find that symmetry fractionalizes. That is, there are certain group relations or certain quantum numbers that are associated with symmetries, and you find you can get new ones. Again, there's a very sophisticated field of mathematics that classifies such possibilities. So here we just look at the 2 simplest symmetries, the global U1 symmetry. And it turns out that, so all the states in the Hilbert space that you originally began with, if you take any finite sample, have integer charges. They have integer number of bosons, or if you have an odd number of spins, then all the spins of all the states are half integer. Whereas if you have an even number of spins, then the spins of all the states is an integer. So we're always talking about differences in charges because the system is infinite. So all of these systems, all of these states in the original Hilbert space have integer charges. But what you find here is you can get half integer charges. The sectors can have half integer charges. And this is again related to the fact that the system, this sector is not on its own. It's just some big region of a really even bigger sample. So in that region, you get a half integer, you get another region with half integer. Totally, it's integer, has to be. But as far as any local operator is considered over here, it has a half integer charge. So in fact, also you will notice here that this assignment, there's no difference between an E and an M. E and an M have exactly the same topological properties, and it's actually really up to you to decide which is E and which is M. There's in fact an EM duality, which is of course connected to electromagnetic duality, so the labels are not an accident. However, once you put in charges, it's conventional to say that the M has charge 0 and the E has a charge 1/2. So now you've made a difference between the 2 of them. And of course, this E particle is what we met last time when we were talking about the RBB state. Imagine you had some resonating valence bond liquid, and then you created a region with a free spin 1/2. So that has half integer charge, and that can live on its own. We haven't established the other properties, but we saw already that the existence of super selection sectors in that very simple argument. There's no local operator that can get rid of the half integer charge. The only way you can get rid of it is by bringing another region with a half integer charge and then combining them. Okay, so we've already seen in a very simple argument how these sectors can exist. Okay. There's also constraints on translations. This also we will derive. So we'll derive all of this in the next 2 lectures, I hope. So it turns out that translations in the original model, when acting on any states in the original model, commute with each other in the X and Y direction. But it turns out that in the M sector, translation need not compute for half integer spin. Okay, so this is a constraint that requires both conservation of charge and translational symmetry. And in that sense, the ingredients are identical to the ingredients needed for the Luttinger theorem of Fermi liquid theory, which we didn't prove, but I stated. The Luttinger theorem also follows from a system that is translation invariant and has conserved charge, U1 charge. So this also has exactly the same ingredients. And in fact, the proof of two can be tied together in a very interesting way. And maybe towards the end of the course, we'll discuss that. But I haven't derived the Luttinger theorem. I will derive this fairly soon. Okay. All right, so those are the general statements about anyons and symmetry and how they tie together. And as I said, there's a lot of beautiful exact results you can obtain by very different methods that I'm going to describe here, and much of which I don't know. But those are mathematically rigorous results that come from very general considerations of what can happen if you have a quantum system with super selection sectors. Okay, so our task today is to quote unquote derive. So we're going to use highly inexact methods to obtain a set of exact results, which are these. And that in some sense is, that's a much harder task anyway. It's in a sense, why I have a job. The job of a condensed matter theorist is to go from this to predict what a given experimental system, will it have super selection sectors and what will be these properties? That's an extremely difficult job, which even the best computers can't solve. But in a few simple cases, that's been worked out. I think it was first worked out for fractal quantum Hall states when you get a slightly different, different set of rules over there. And I'm going to work it out for the RBB state, the Z2 spin liquid today. Again, using a set of steps that are very familiar and in quantum field theory. We just follow them through and carry them through. Systematically, you will get those rules. Okay.
So
yes.
Is there any difference between the models where S is half integer and F is integer?
Yes. So that's what this. So yeah, let me also clarify this. 3 different S's floating around. Their difference is clear in the notes, but not so clear on the board. So there's the operator S, which I have write with a vector. So that says it's a generator of SU2. And the square of this is S into S plus 1. And so S is integer or half integer. Okay, so this little S I've written, this S I've written in orange, at least in this board. Okay. Then there's a little s, which always have an alpha index, and that's a boson. That's a spin a half boson. Okay, and the answer is yes. So these anyons can exist both for integer or half integer x. So in principle, even for integer boson density, you can get a non-trivial insulator. So we met a trivial insulator for integer boson density with just a one boson per site. But there could be a more complicated insulator even for integer boson. And that for that, there is no such constraint. This will become they can commute. But it can have these equations.
That equation is amazing.
But what you see from this is that if you had a density of boson which is half integer, then there is no trivial state, because in no trivial state could these commute. So there's a no-go that you can't have a trivial state at half integer density. But you can certainly have it in any other integer density too. I should say this anti-commutation only applies in the M sector, not in the others. There can be very complicated realization of translations, even in the other sectors, E and epsilon. And there's many papers classifying those. That's in the condensed matter language, that's called working out the projective symmetry group of the spin-ons. Okay, it's a tedious task, but there's, I think Wen was first wrote down a whole set of possibilities on the square lattice, and invariably with all of these possibilities, there's always new subtle ones that people discover. I don't think there's a full classification of all possible symmetry fractionalizations for given super selection theory. All right, so now I've just, yes, question. Is there a question? All right. Okay, so I now I've written here what I wrote down last time. I take this particular model. I'll just take, for simplicity, a model on the square lattice or the triangle lattice with nearest neighbor exchange. Now, literally, those two models are known to not be in this system, but there's a broader class of models where you add further interactions, which now we know today are in this class, but the analysis is exactly the same. So I'll just imagine that they could have existed in this class. There was a hope that they could have in the early days, but that turned out not to be true. It was just nearest neighbor interactions. All right, so you look at the partition function, and you can rewrite the partition function with no further approximation as a path integral over three fields. Si alpha is a spin-half boson, the Schwinger boson. So the relationship between this capital S and these little s's is 1/2 Si alpha, dagger sigma alpha beta, S where sigma are the Pauli matrices, and a vector over there. Okay, so you make that decomposition. You have a constraint on the S bosons on every side. It's 2s, and let me make that orange. Okay. And that constraint is imposed by this Lagrange multiplier lambda, which is this constraint right here. If you do the integral over lambda, you just get that constraint. And then when you insert this in here, you get a 4 boson operator, and you decouple that 4 boson operator by a Hubbard-Stratonovich transformation. And that field you introduce lives on the bonds, and that's the Qij. It doesn't have any spin indices. All the spin indices are only in the bosons, and Q is just a complex field that lives on every link of the lattice. Okay, and this particular action has an exact symmetry, a gauge symmetry, where you can change S, Q, and lambda in this way, where rho sub I is an arbitrary function of position and also of time. All right, any questions then? So now what we're going to do is we're going to just play with this pattern. We'll do really the standard bag of tricks, look at saddle points, look at fluctuations about saddle points, look at non-trivial saddle points, look at tunneling between saddle points, and sum over saddle points. So once you go through that entire task, you will derive every one of these things over here. Okay, and you can make that sort of systematic by taking certain large N limits, which are actually done in the notes, but I'll pretend that I'm working with SE2, at least on the board. And so everything I'm doing is uncontrolled. But it's at least systematic. There's a route that we're following where we're just trying to evaluate this path integral by the standard rules of identifying saddle points and then summing over the saddle points and fluctuations about them. No, the large, if you take large S, this large S, then you just get ordered states. That doesn't work. Then you don't get any of these states. Okay, that's what was the Holstein-Primakov or Dyson-Malloy bosons I introduced a while back to describe the antiferromagnet. That appears in the large S limit. And so the Holstein-Primakov bosons, the Dyson-Malloy bosons, can be formally justified in a large S expansion, but they don't give you any of these states. Yes, was there another question?
Yeah, how does one see that the measure of the path integral is also invariant under the gauge transformations?
Okay, well, I think it's, since these are very simple changes of phases, so the change of phase clearly is invariant. So now there is, this is just a shift, so I think it's all okay. Yeah, I haven't fixed the gauge yet, but at the moment, yeah, so this is, let me, better answer is the following. since it's a compact group, since I'm just, these are phase factors that go from 0 to 2 pi, I can just integrate over the full set of possibilities, and I don't even need to fix the gauge. I just sum over all of them. This gives me an overall constant up front. Yeah, I think that's the better answer for now. We're on lattice with a compact group. Then just like in lattice gauge theory, you don't even bother fixing the gauge, you just integrate over all gauges.
For small s and q, I can see that, but for lambda, the transformation, I cannot see that very easily for lambda.
Yes. So what is the question?
For small s and q, there is the transformation is only in the phase, and if I integrate over all the phase, I get the same contribution from the action. So there is an overall constant that I can see. But for the lambda term,
so there is a slight subtlety here. I mean, I'm integrating on lambda from minus infinity to infinity, but there is one subtlety that see lambda, everything has to be periodic and going to 0 to beta. So you have to. So there is a special part of lambda to keep track of. So when you're doing this gauge transformation, you have to just make sure that lambda remains periodic too. And so that puts certain constraints, but it won't matter for things you're talking about now.
Okay.
Have a finite system and temperature is finite, then you sometimes have to worry about that. But for now, I won't. But later on, I mean, once we fix the gauge, when you take some continuum theory where we don't have a lattice and there are certain infinities associated with the gauge, if you just don't fix it. But when we get to that point, we can really borrow the standard techniques from quantum field theory to fix the gauge. Yeah, again, for abelian gauge theories, it's simply very simple. At least the level we're going to work on it. We pick the Landau gauge or some of those gauges. And there's really no ghosts to worry about. At the order will work. Okay, all right, great. So let's just turn the crank. Imagine we don't know much. All we learned is mean field theory and Gaussian integrals around mean field theory. And ultimately, that's all you need to know. Okay, so the first step is we're going to take the saddle points. And we're going to look for saddle points in Q and lambda. Oh, look for. Saddle points with Qij, which is a function of tau, is an arbitrary function of position, but independent of tau. I call that Q bar. Lambda I here, I lambda I of tau, that piece of lambda bar. So what in terms of lambda, the one way to think about it is that here's the lambda complex plane. I'm integrating over real lambda because I need to integrate over real lambda to impose the constraint. What you find that the saddle points all live in the complex plane with an imaginary part. It's in the lower half plane. I lambda. This is positive, so this will be here. So what you're going to do is you have this contour you're integrating over. You're going to distort it and integrate it like this. So this will be where our saddle point is going to be. But so at this point, you can just forget about this I. But when you're doing the fluctuations, which we won't do, but people have done such things, then you do have to go along this axis. Okay. So now if Q and lambda become constants, then the remaining path integral for S is a very simple problem. It's just a you can write it better to think of it as a Hamiltonian problem. So then you have a mean field Hamiltonian or a saddle point Hamiltonian for every Q and lambda. So it's a function of the Q bar and the lambda bar. It's just a regular Hamiltonian of bosons with some twists. So there's a term which is completely on site, lambda bar, someone I S tag I alpha, it's alpha, and then there's that term over there, minus Qij star with a bar now, epsilon alpha beta, yes, B. Plus summation congregation.
Probably that's J.
Yes, the J in front of it. Yes, thank you. It's not in front of lambda. All right, so our task is basically very simple. You give me a Q bar and a lambda bar. I just have to determine the spectrum of this Hamiltonian and find its ground state energy. This is a kind of Hamiltonian we've met many times before. It's the Bogoliubov Hamiltonian, like maybe even the first few lectures. It's got some boson B dagger B terms and a BV term. So we met it in spin wave theory, we met it in superfluidity, it's the same. And we met a fermionic version of this in the Bogoliubov Hamiltonian for superconductivity. Okay, so in general, we know we can diagonalize this. And you get some set of Bogoliubov operators. And so you can say without much trouble that there will be some, and we're going to look for saddle points that are translationally invariant, but in principle, you can diagonalize this even for non-translationally invariant Hamiltonians. So you'll get some omega, some set of eigenvalues. Let me not even assume translationally invariant for now. You get omega mu, some set of numbers Q bar that depend on Q bar and lambda bar, times some gamma dagger, mu alpha, gamma mu alpha. So these are some new bosons that you obtain by the appropriate Bogoliubov rotation. If you want to see it actually done in detail, I think it's in the notes. All right, or maybe it'll be a homework problem. Okay, so having done this, and there's also, actually, you do have to keep track of the ground state energy. There'll be some ground state energy here of Q bar and lambda. Okay. And these omega mu will be all positive. I mean, if they're not positive, then you're in trouble. The bosons will condense, and then you can't think in terms of excitations about some saddle point. The saddle point will not make any sense at that point.
Sorry, stupid question. I forgot. What does the index mu run over?
So it'll run on the number of sites or something, the total number of bosons you have.
But you can think of it as momentum, isn't it?
Correct. Yeah, if you have translation invariant, it'll be momentum. Okay. Right. There's some subtleties with K and minus K. Actually, in this case, there aren't. Yeah, it is literally the number of sites. All right. So we can solve the mean field Hamiltonian for Q bar and lambda bar, but what determines Q bar and lambda bar? Well, there's two ways to think about it. One way to think about it is you must pick your lambda bar, which also could have been a function of position in principle. You must pick lambda bar so that S dagger I alpha, Si alpha on every site is equal to 2 times capital S. Okay, so you must pick lambda bar for that to be satisfied. And once you've picked it, in fact, all you can do is pick a Q bar that minimizes this energy. That's one way to see it. The other way to see it is actually very simple, just from the original Lagrangian. Just take a saddle point of the Lagrangian. So this equation here is nothing but the equation that d by dl over d lambda I equals 0. So if you take the derivative of the action, Lagrangian, sorry, it's whatever gives you the action after a time integral, you get this combination here. And then in the path integral, that means that you replace that operator by the expectation value. And this expectation value is evaluated in this Hamiltonian. And in exactly the same way, you take d by dq of L equals 0. And that gives you, I don't want to erase that yet. That will give you the other equation, which is the same as the equation of minimization of the energy in this case. But for lambda, it is not a minimization equation. So d by L by d equals 0 give you some Qij, expectation value of epsilon beta star there in the mean field Hamiltonian. That comes from those two terms. So this is really very canonical standard Hartree-Fock mean field theory combined with the Vogel-Leibler rotation. Something we've seen several times so far. Okay.
Question?
Yeah.
Can we see it, if we track the original gauge symmetry, what happened to it?
Yes, that's exactly what I'm going to say. Yes. So what's different about this mean field theory, unlike the other mean field theory we met? Well, what's different here is that if you look at this mean field Hamiltonian, there's no bare term, bare kinetic energy term. The S bosons can't move without this new thing that you put in. Usually this Qij comes from the from some interaction term or quartic term. In fact, that's where it comes from. But there's no bare term, but the S bosons could move on their own. So that's a big difference here. And one consequence of that is that the set of Qij that you pick to solve these equations are not unique. So if you give me, you work very hard, you give me a set of Qij and say, these solve these equations, I can give you another set. I can give you another set for just making this gauge transformation, provided the rho I are time independent. So I just pick any set of rho I and rho j. I'll give you another set of Qij, which will have the same eigenvalues, the same value for omega mu, and the same value of the energy. So that's what this gauge invariance guarantees that. Okay, so another way to say this is that EMF and omega mu depend only on products like this, on even loops. Qij, Qjk star, Qkl, dot. You pick some loop on the lattice, any loop you want, as long as it has even number of legs. You put a Q star, Q star, Q star. That's the flux you have to measure. And the answer, and if instead of giving you the values of Q, what I should really give you as an invariant statement is the product of all these Qs for every loop. And that's the unique information I have. I don't have information on what the Qs are. That's totally an artifact of my choices of gauge. But these are gauge invariant statements, which tell me something about the saddle point. Okay. So I have to find, so when I'm solving these equations, I should be careful to just look for different values of these Qs on the different loops of the lattice. Okay. So these will be some background fluxes that will determine the nature of the ground state. And those background fluxes will then end up determining, so these gammas are in fact precisely the E particle. They carry spin a half or charge a half. And they could have very peculiar properties of their translations. And that entirely depends on the set of Qs you pick. There could be some fluxes, so they could have non-trivial realization of the translation operators. Basically, the point here is that you get some set of gammas. The wave function of the gammas are highly gauge dependent. So when you make a translation, the action of the translation will give you the same state up to a gauge transformation. However, that gauge transformation you have to keep track of to figure out the full algebra of the symmetry operators. So that's why you could have strange factors appearing here because these spin-ons or these superselected sectors are only defined up to a gauge transformation. Yeah.
So if I'm trying to translate this into particle physics.
Yes, please go ahead.
It seems to me like your Q
Yeah.
includes both what we would call the lattice gauge field. The free phases are like the lattice Higgs field. I mean, the
Yeah.
Goldstone bosons, and the absolute magnitude of Q is like the Higgs field. Is that
Well, you're almost there. So it actually depends on the lattice. So yeah, but that's exactly the point that I will now discuss eventually. On the square lattice, it'll turn out the Qs are like gauge fields. But on the triangular lattice, they have a dual existence. Some of them are like Higgs fields and others are like gauge fields. So this is what you have to figure out by looking carefully at the structure of the saddle point and the structure of these gauge transformations.
Hello.
And all of this fun stuff is precisely related to that. Yes.
Yeah, so you mentioned that this EMF and omega mu depends on even loops. So after finding out this effective or Bogoliubov Hamiltonian, do I need to minimize this EMF and omega mu over these loops to find a true ground states?
Correct. That's what you need to do.
Ah.
Yeah, you need to take the set of all possible loops and assign Q some number to the product. Pick a set of Qs and each that will give you some set of products. And that's the only information you need. And over the set of products, you have to minimize the EMF. Yeah. So in general, not an easy task, but has been carried out from some simple lattices.
So the follow-up question is that, I mean, can we guess the structure of these even loops based on symmetries that will
every even loop is a gauge invariant object.
Oh.
Every loop is a law. Typically, you take some very small loops and you're done. But in principle, you could have Q. So in this particular, right? So here I'm taking a derivation based on a path integral method. So in the path integral method, I only get Qs on nearest neighbor sites. But if I took a more expansive point of view, I say I'm just doing variational calculation, then in the variational calculation, you're certainly free to take Q as your even on longer bonds and any bond you like. And once you fix a set of Qs, you can take all possible loops with those Qs.
Okay. Yeah, thank you.
Right. All right, so let me just tell you the answer for the square lattice and the triangular lattice, which are the most important cases. And let's see.
Hello.
Yes.
Yeah, in the earlier case, when we discussed the Bogoliubov Hamiltonian and the ground state of that Hamiltonian, there was a Bose condensate that allowed us to not worry about the exact number of particles, right?
That was the total number of particles. Yes, not the number of particles.
Even though it was conserved, and in the mean field approach, it seemed like it might get violated, but there was a condensate that allowed us to not worry about the exact number of particles in the excitation of the vacuum.
Right.
Oh, so is there such a thing here?
So here we're assuming there's no condensate, and that's simply related to the fact if there was a condensate of these bosons, you would break the spin rotation symmetry, and the condensate would then end up describing an antiferromagnet, not a spin liquid. But the other point, so there's no condensate, but it raises another important point that you mentioned, which is the question of conservation of number of bosons. So this Hamiltonian doesn't conserve number of bosons, okay, but however, we know that you have this exact constraint, S dagger S must be 2S on every side. So those are the physical states. So here we've made a much more serious approximation, which is why many of these mean field theories look very suspicious in the early days. So we've made a much more serious approximation is we have ignored the fact that the number of bosons is conserved not just globally, but locally. So for the Bogoliubov theory, it was not such a sin, because who cares about the entire system that it's exactly the same number of particles? maybe you're just looking at some very large subsystem, and in that subsystem, things are not concerned. But if this is here, it's much more serious. It's not a question of global conservation; it's a local conservation, and we're ignoring it. And we can't ignore it. That's really something we have to worry about. And in this language, this means that we have to worry about the integral over the lambda I. Or in other words, we have to worry about gauge invariance. So lambda I will look like the time component of a vector field, gauge field. And so we do have to worry about the path integral over the gauge fields. And once we do all of that properly, then you'll get these properties here. But that's a very good point. Okay. Right, so yeah, but important point, we are making a much more serious mean field theory here with some rather crude approximations that you should be very skeptical of, which are much more serious than for the Bogoliubov theory. Okay, and people were skeptical, so that's why presumably, we needed Kitev's exact solution to convince people that what was being done here was okay.
What's the role of the SU2 of spin symmetry here? It's not in your answer.
Yeah, so for now, I'm just assuming, well, the fact that these are degenerate and don't depend on spin, I think requires SU2. Otherwise, you can get a slightly different spectrum.
Imagine you have only one alpha. You just take the same Hamiltonian.
Yeah.
That you wrote, and you have only alpha equals 1.
Well, you have to have two of them, otherwise, you can't just fractionalize one boson. Then this constraint becomes kind of trivial. There's nothing to do.
That's from the starting point, but you could have taken that as your starting point.
Well, the starting point could have an XXZ Hamiltonian. If you remember that SX have vector X, the XXZ model. Then everything would go through except the spectrum one may have some spin dependence here. But there'll still be two values of alpha. You can't work with one value of alpha. That's kind of a trivial problem. It's just that, okay, yeah. It's not, I do need the U1 symmetry for some things. But in fact, most of what I'll say, except this very last part, goes through if I had no symmetry whatsoever. All right. In fact, for the Rydberg atoms, if you heard my talk yesterday, that's what you need to do on Monday. Okay. All right. So yeah. So now let me give you the answer. What is the set of Q's and lambda that satisfy these equations? So on the square lattice. And the triangle, they are really very simple sets of solutions. I mean, all the Qij, the magnitude of the Qij bar is just some Q, called Q bar. It's the same on every site. So the only thing you have to worry about are the phases. And they're also real. You can always choose them to be real. At least in this case, there could be other more complicated cases within the global minimum, they're not real. Again, that can change a few things, but let's just look at the very simplest case. So all you have to do, I have to tell you, is the signs of these Qs. And so you just take some, for the square lattice, take a set of signs, you have to just take some orientations, and basically you get, it doesn't matter, it's very simple. You can take them. That means, what do I mean by that? Yeah, okay, so one more thing I have to tell you that Qij is equal to minus Qji. So there is an orientation. So the arrow tells you which orientation is it positive. We get something like this, and for the triangle lattice, there turn out to be two possibilities, but the one that has a lower energy looks something like this. Yeah, you just take the horizontal ones going in the same direction, and then you do the same for these ones, when you pick the direction like this. So there's some, so these arrows tell you what the sign is, which orientation is positive, and they all have the same value. Okay, and then from this you can determine omega mu. I can tell you what the omega k are. The omega k turns out to be square root squared minus j squared q log squared times some on alpha sine k alpha whole squared. And what is k alpha? Let me call it k. Let me call it k sub p, right? Yeah, p. P different. So k sub p is the vector k dotted into EP. And what is EP? Well, EP for the square lattice is just these two vectors. And for the triangle lattice, obviously it's these three vectors. Okay. All right, so you get some solution, and this has some interesting structure that you can study. And of course, you should just keep in mind that this dispersion is very much gauge dependent. There's a certain gauge choice you made in assigning these signs. And so the dispersion can change. It's not really measurable directly, but important point here, it has a gap. It's always non-zero for every k, and that's an invariant statement. So this is a gapped state that we have obtained as a saddle point of this particular path integral. Okay. Yes.
On the square lattice, it looks like sort of a trivial configuration on each square. On the triangle lattice, you seem to have a flux in both of them.
But you're not allowed to take an odd number loop.
Oh, so what's the invariant connection?
It's all of these ones.
Those are all possible, right?
Yes, yeah. So they're in this case, yeah, but actually you're right. I think the Kaggle, I've forgotten now. On the Kaggle main, it turned out to be two bosons. There is another solution possible on the triangle lattice too. That's right. That was obtained by Vishwanath and Wang. Not this one. There's another set of configurations. But yeah, there's no trivial fluxes. All the fluxes are trivial. These are all positives, the Qs.
That's why you simply have an ordinary momentum spectrum here.
Yes, yes, yeah. If you have the Pij that you asked about last time, Nadi, then you could take odd numbered loops of those, but the essential structure doesn't.
That would be an ordinary gauge.
Yes, right. All right, so what we have determined here is the full, for a certain ground state, you've determined the spectrum of the spin-on excitations, which are these E particles. We haven't seen any sign of the others. We'll get to those later. And of course, the one we have, so at least got half of the anyons. They have spin a half. They can have rather complicated problems under properties under translations, depending upon the set of QIJs. In this case, they're fairly simple, but that depends on exactly the details of the Hamiltonian. There's no general constraint on them from first principles. Okay, so step two then, I shouldn't have erased that glorious path integral. We found a saddle point. Now we have to do fluctuations. Okay, so we're going to do that in two steps. First, we'll do small fluctuations. I think that will end up answering Tom's question. And then we'll look at large fluctuations with new saddle points. And that will give us the other sectors. So let's do small fluctuations first. Now, in this case, the full set of fluctuations of all the Qs and lambda to quadratic order and do the path integral numerically, that actually has been done for the triangular and square lattices. The triangular lattice by Christian Batista and collaborators. But we're just going to focus on an important sector. So most of the, when you diagonalize the quadratic form of fluctuations, you get a whole bunch of gap modes. But the question really we want to ask, are there any gapless modes in the fluctuations? So we look at fluctuations. So formally, what you really should do, you write your Qij, it's Q bar, Ij plus some delta Q, and lambda bar, I lambda is lambda bar, is I delta lambda, and then you get some action, S fluctuations, be delta Q of K and omega, delta lambda of K and omega, matrix, delta Q delta lambda, and this will be some function of K and omega. So you find this function of K and omega, and then you find its eigenvalues, and then you sum over all the eigenvalues to give you the correction to the ground state energy or any other property you want. But that's a very laborious and difficult task for this particular model. It's something you can do without too much trouble if you had a field theory with all kinds of symmetries. But here, this would be years of work for a good graduate student to work through in all detail. All right. So what you'll find when you do this, we don't want to go through all of that work. We just want to ask, is there some very special axes in the space where this thing vanishes for some omega and k? In other words, there's some omega and k where you get a pole or a zero energy excitation. That's the question we would go to. It's a limited question that we ask. So in general, the answer is, it's not going to vanish unless something special is happening. There must be some special constraints that leads to a zero eigenmode of this matrix. And what is the constraint we have on this? Well, the only constraint we have is gauge invariance. So let's just focus on the part that are interesting as far as gauge invariance is concerned. And in fact, I'm going to look at time independent gauge transformations. I'll fix the gauge so that you can always fix gauge that lambda is time independent. So anyway, okay. So I'll just look at the following fluctuations. And for now, you can consider them time independent. For this particular action, I'm going to take the Qij, write it as Q bar times exponential I call it the big theta Ij in the notes. And so I'm going to ignore fluctuations in the magnitude of Q. I'm also going to ignore lambda, but just look at the fluctuations of this time-independent fluctuation of theta Ij. All right. So now there's a constraint on the theta Ij, which is because the gauge transformation acts only in the phase of Qs. So that gives you a constraint on theta Ij. So theta Ij have to be invariant under a certain transformation, which I'm going to write in momentum space. So let me look at, since everything is nearest neighbor, I turn out to have three theta of thetas of p will be theta of I to I plus p. Where p is, of course, these are the EP that I showed you for the square lattice and for the triangle lattice. Okay, so there's two thetas for every side of the square lattice and three thetas for every side of the triangle lattice in this simple model. And under gauge transformation, what you find, you get theta p goes to theta p, sorry. theta p of vector k to theta p vector k minus 2 times rho of k, where rho of k is an arbitrary function of k, times cosine k p over 2. Where kp, of course, is k dot et. Okay, and you can do this for second neighbor couplings, fourth neighbor couplings, whatever. Every coupling will introduce a new vector e, and you'll have a similar gauge transformation. This is just coming from qij goes to qij rho I plus rho j.
Sorry for being picky. This is probably an error rather than an equal sign.
Thank you. No. Thank you. We're not being picky. So that's the gauge transformation. This is the same arrow as this one. That arrow. Okay. So whatever action we get, it should be invariant under this transformation. So this tells us that the action delta S here, S fluctuations, I can say that S fluctuations is only a function of what I call IPQ, which will be cosine kp over 2 times theta p of k minus cosine kq over 2 times theta p of k. Yeah. Sorry, that's important, so I should write it out more clearly. Yeah, let me write it out over here. I don't need this. So I find a set of gauge invariant objects to linear order at all momentum. These are the IPQ. And these objects are invariant under gauge transformation. And something like cos kp over 2 q, no, sorry, theta p k minus cosine q over 2 times theta p, this is a q. And of course, this, nothing shocking here. This is like a vector field, or I mean, it's both, as the question Tom asked. I'm sort of combining two things here. One is the transformation of a phase field, and the other is the transformation of a vector field. We have to figure out which is which. This is a more general way to write it, general momentum. And this is, of course, the analog of a flux. It's a gauge invariant object, and it's equal to this. Okay. So what we want to now find are points. We're interested in points where all of these vanish. So if these vanished, then this IPQ would vanish. And so your contribution to the fluctuation action would also vanish, because the action, so delta S or S fluctuation, I mean, we can guess. We'll have a term like, sum on k, some lambda of k, which we don't know what it is, some general function times IPQ squared of k. It must be of this form, because we're only going to quadratic order. This is a quadratic function, and this is the most general quadratic function that's invariant under this transformation. Okay, so the only assumption that this is a smooth function which doesn't vanish or have any poles, and that you have to verify by explicit calculation. That always turns out to be this lambda of k. There's nothing special, it's just some constant you will get, because you're really expanding about a gap system. So it's the analog of the electric charge of the Maxwell term, or the kinetic energy of the scalar field, depending on what values of IPQ take. All right. Okay, so now, so far very general. All I've just put is some constraints on the small fluctuations about the saddle point. So really the question we're trying to ask here, another way to say it, is you started out a gauge theory, so U1 gauge theory on the lattice. And you're trying to ask what phase is this gauge theory in, at least perturbatively. So perturbatively, we know gauge theories have two possible phases. You can have the photon phase or the Coulomb phase where there's a gapless gauge boson, or you can have the Higgs phase where the gauge boson is Higgs. We're trying to ask which phase is this in. We don't know. It's the gauge theory. It could be in either phase, and that's which phase it is in is a gauge invariant statement, because it's a statement about the nature of the spectrum of quadratic fluctuations. You know, when you have the Higgs phenomenon, you get a vector, massive vector particle. If you have the Coulomb phase, you get a photon, which has only two modes. Those are two different realizations of the low energy states of a gauge theory. And we have no idea which one we are in. And that's what the IPQ is going to tell us. Okay, so here, there's a divergence between the square and triangular lattices. Because for the things, let's just talk about the triangle lattice, square lattice first, which we'll find is in the Coulomb phase, at least perturbatively. And the triangle lattice we'll find, that's the one of interest to us. It's in the Higgs phase, and in fact, we'll realize all the other fun stuff over there. So let's talk about square. So the question invariably becomes, because you want this to vanish, so we can find some very special wave vector K, which are called G. That's that. IP of G is equal to 0 for all P. Okay, so you have very simple, your EP had two values. So this is simply a very simple equation. You want to find cosine gx over 2 equals to cosine gy over 2 is equal to 0. And there is a solution. So this gives us, the G is the wave vector pi pi. So that's in fact a signal that there's a photon here. The thing vanishes, and it vanishes at wave vector pi pi. And that's telling you that the photon or the gauge transformation in the continuum limit that's going to give you the photon is the staggered gauge transformation, where you assign bosons, spin-ons on one sublattice to have positive charge, and the spin-on on the other sublattice to have negative charge. That staggering of gauge charge is what's specified for this pi pi. Okay, so let me make that more explicit. Yes.
What happened to the index Q? So you have P?
I look in which index Q.
So
IPQ has an index.
they should be for all P and Q.
Thank you. Yes. P has to be not equal to Q because it's 0 to the otherwise.
Sometimes symmetric.
Yes, yes.
So P and Q are lattice directions.
It's the set of bonds, but for nearest neighbor model, yes. So the triangle lattice has 6 neighbors, but of course, one can be translated to the other, so it's 3 neighbors, right? But the Kagome becomes a bit more complicated and so on.
So can we interpret I as the field strength?
Yes, for this case, which is what I'm just going to do now. So now let's just take a K.
Don't we have to check it's not pure gauge?
Sorry?
So there is some configuration where I is 0, right? But we also, in principle, we should check that it's not a pure gauge.
Yeah, that's exactly what I'm doing now. So now you take K equals to G plus Q. The Q is small. Okay. All right, so what happens then? Well, you just plug it in here and figure out what this is. There's only one non-trivial I, which is IXY of Q. What you'll find is just QX theta Y minus qy theta x. Okay. There's your photon. There's your Maxwell term. And the action is just IPQ squared. And you figured out the coefficient of the fxy squared term. Okay. This is fxy. And we have our photon, which is theta. So now, what very important thing here, sorry, yes, this is one very important thing. This is K. And, right, okay, this is theta y of K. So, or G, really, if you wish. It doesn't matter at that order. Okay. Okay, so the point here is that the gauge field, what is the gauge field? If I want to think of this as a gauge field, the gauge field, we like to think of the gauge field as having momentum Q, but this theta field really has momentum G plus Q. So there's a shift that you have to keep track of. So in this case, this is the kind of messy stuff that condensed matter theorists constantly worry about, but it's confusing to someone living in the particle physics world. But the point here is that I can now say that theta p, if I go to X space, I'm going to call that a gauge field based on P of X, but there'll be a vector X. But there's a factor here, which is e to the I G dot X, which comes from the shift. So my actual gauge field is not theta. It's the staggered version of theta. It's plus on some bonds and minus on other bonds. So this is always plus or minus 1, which is good. So that tells me that the spin-ons, it's easier to say this in terms of charges, gauge charges. So the S here is a plus, minus, plus, minus. And these are the gauge charges of the spin-ons. Yeah.
If we go back to the original model, I
Yes.
think the reason you got these things is if you could have started and just take all the odd sides and replace S by S dagger,
Yeah.
then it would look more like a standard gauge field.
Correct.
Then you will not have to worry about all these signs.
Yes. Yeah. I mean, so that's in fact what was done, and in fact in the notes I do it that way. I'm trying to present, at least in this lecture, a way of getting at the answer. If all you did was just close your eyes and just did a very analysis just based on gauge invariant, just without
But in
too
fact,
much.
when Tom asked his question,
Yeah.
but why don't you just flip the name of S to S dagger?
Yes, but as you can see, all now for the triangle lattice, you can't do that. There is no sublattice structure, and I'm just trying to see how that emerges just from this analysis based on the IPQ. All right, so now we have a photon, and so in terms of this, we can say now that delta S without, and also similarly, let me say, you also take lambda or delta lambda of I of X, and that becomes some, again, e to the I G dot X times some A tau. And then your action, we know that for small fluctuation, there'll be a sector of the action, which will look something like this, where delta S will be some constant K1 over 2 times fxy squared, plus some other constant K2 over 2 times f x tau squared x plus y tau squared. So there's your photon. And it's just a matter of determining the values of K1 and K2. Things I can say I have done once in my life. Do it for this problem. These are some numbers that you'll get from all these dispersions that you had before. Okay, so now we've, in a sense, we found this is a dangerous thing. We took a saddle point and we said this is a good saddle point to work on. And initially, when we looked at the spin-ons, we were very happy because everything was gapped. So maybe this is a good saddle point. But now we looked at fluctuations of the other variables, and you're finding a gapless mode that we need to worry about. So this gapless mode introduces long-range interactions. And so now there's a question of what is the fate of this long-range interaction? Yes.
Is there any material with a candidate for this long-range interaction?
In 3 dimensions, yes. So in 2D, as I'm just going to say, you also have to look at non-perturbative effects. They're monopoles. So I don't know, we may talk about that later. This is the reason I'm not talking about the square lattice now, because actually the square lattice, even though it starts out really simple, becomes much more complicated later. And because there are not just photons, but there are also monopoles, which are instantons between different flux configurations. And those in this system generically will make the whole saddle bond unstable, leads to what we call confinement. But then you have to worry about the fact that this is a system, at least for high integer spin, which, there's general arguments that they cannot be a trivial ground state. So how can you get a confining state, which is trivial usually? But then you find that when you keep track of various Berry phase terms, it's not trivial. There's a broken translational symmetry. Okay, so there's a whole field that developed. This was something that Nick Reed and I figured out in '89, at least the first steps of it. I think afterwards there was a hope that perhaps there's some special point, some gapless point where even the matter fields are gapless. Unlike this saddle point I'm describing, there are other saddle points you can look at where the matter fields or the spin-ons become gapless. And maybe there's enough gapless matter fields to stabilize some kind of phase which starts from this photon description. That becomes some kind of conformal field theory. But that becomes a complicated issue of does a certain conformal field theory exist? And I think the evidence as of 2 years ago is that no, but all right, so that's still an ongoing story, as you can see. There's a lot of rich physics on the square lattice on what happens once you have this photon. And I've probably spent too many years of my life worrying about this problem. But anyway, it's been great fun. And but that's not what I want to talk about today. I have 15 more minutes. The other case is the triangle lattice, and where things turn out to be much simpler. And I think we know the answer, at least in principle, the structure of the full non-perturbative answer, which I just wrote down up there. So let's try to move in that direction now. Okay. All right, any questions on the square lattice and what we've done here? At least we've done something nice. We've shown the existence of an emergent photon. And in answer to Edward's question, in 3 dimensions, the photon phase can be stable because of there are no instantons of that type. The Coulomb phase is stable. We live in a Coulomb world. So there could be a stable phase, and there's some indications of these photons in higher Claude lattices, but it's not experimentally. That's ongoing work of great interest, but I don't think theoretically it's clear there are such phases. Yeah. Okay, but we're in 2 dimensions in the cube trace. Yeah.
I already asked you, if you just did the CPN model,
yes,
the way it's done on the lattice,
yeah,
don't you get the same photon?
Oh, yes. Yes. So what's different about the CPN versus this model? It is in the continuum limit, essentially the CPN model, when the spin-on gap becomes very small. Well, what's different is the background charge. So there was this term. Roughly speaking, the CPN model, that's 0. There's no net charge there. You're just expanding about a charge, a vacuum that has 0 charge, and then you have the CP1 field that are the gap bosons of the unit charge or half charge, whatever. Here there's a background charge. And what this means is that when you put in monopoles or instantons in this, you add instantons to the CP1 theory, 2 + 1 dimensions, they have non-trivial translational properties. They're not trivial in their translations. And that changes the continuum limit of the monopole. So I'm sorry I apologize to some of the students. I'm using a rather advanced language here, but maybe eventually we'll get to it. So if you start from CP1, CP1 theory, SCP1 is some Lagrangian of CP1 that you know, that d mu minus I mu z alpha squared. Okay. But then you want to add some source terms, lambda, to some monopole operators. These are monopoles of some charge at some position x. So you want to add these terms. And what happens is that because of this 2s, these monopoles come with.
It's not the same lambda.
No, this is some other lambda. Why? Okay, that's the fugacity for some monopoles. And I should really put it. You have to be very careful. You have to put it on a lattice. So these y sub I have some phase factors. So the continuum limit is much more complicated. Basically, when you take a monopole around a site, it's got to pick up a flux, which is related to this charge. So that's absolutely crucial for showing that the confining state is not trivial. If you didn't have that, the confining state would be trivial, and you end up with a contradiction. Okay, so that was probably very hard to follow for many of you, so don't worry. But a problem close to my heart, of course. All right, so 10 minutes. So let's at least try to make some of the steps for the triangular lattice, where fortunately life is much simpler and things were figured out pretty quickly. This story is still ongoing on the square lattice. Okay, so now we go to the triangle lattice. So now there's three IPQs. So this is E1, E2, E3. And you have I12, I23, and I31. You have three invariants that you make out of these three thetas. Okay, where IPQ of K okay, so then you ask for, is there a K? Is there a K where cosine KP over 2 equals 0 for all P, for P equals 1, 2, 3. Okay, easy problem to ask. It's plotted on Mathematica, answer is no. There is no K for which all three of them vanish. You can only make two of them vanish, but not all three. Okay. So at this point, you can just declare victory and say, aha, there is no gapless mode, there's no photon, and proceed. But you might, no, but to understand a bit better, let's imagine that, you know, the lattice wasn't perfectly triangle. It was like a distorted square lattice. So suppose I had a lattice like this, which has the same topology, the same kind of analysis to go through, but I had some weak couplings along these bonds. Okay. Suppose I was looking at this lattice. Everything would be exactly the same because the connectivity of the lattice is exactly the same, the triangle lattice. But in this symmetry, if this is the real material, this bond would be weaker than that bond. Okay. So let's call this the one in the two direction, and this is the third direction. So you can see maybe it's good to make I12 vanish, but let me not so much insist on I13 and I23 vanishing, well, because that costs less, it's smaller and there'll be less energy cost. All right, so So we're going to pick thing so that the cosine k1 over 2 equals 0 and cosine k2 over 2 equals 0. But not k3. So we just pick that in this case. Just to proceed one further step. You don't have to take the steps. You can just work with the original theory. But this, I think this clarifies some things. So on the triangle lattice, all right, all the nodes are here. You write k, you pick a wave vector g. This is what I called g previously. If this was actually your lattice, g would be still pi pi. In the full triangle lattice, it's something slightly different. The g is 2 pi over root 3, 0, 1, you pick that. And this has the property that g dot e1 is pi, g dot e2 minus pi, and g dot e3 is 0. All right. So now I have the action. I have to look at the action, which is I12 squared plus I23 squared plus I31 squared. What does the action look like? So I'm going to take the continuum limit as before. I'm going to say so I have three thetas, theta of r, theta 1 of r, theta 2 of r, and theta 3 of r. So they're all going to be near the wave vector g. And so I pick them the following way. I call it b1 of r, that's e to the I g dot r. And I really should put the I there because theta is real. B1 will also be real, but this also has an I in it for that choice of G. You can check. Okay. On every lattice site, minus I B2 of R, G dot R. And this I'll call H of R. These phase factors, these are just constants, with ones in front of them, plus or minus 1. Okay. All right, so then you figure out what the invariants are. And so then what you'll find is I12 squared plus I23 squared plus I31 squared is equal to del 1 H minus 2B1 squared plus del 2H 2B2 squared plus del 1B2 minus del 2B1. But these are derivatives along those 1 and 2 directions. Okay, so now that should look familiar. So now I have a gauge field, which is B1 and B2, but I also have the phase of a Higgs field, H, and it has charge 2. So I'm in a Higgs phase. So I think you tell me that this theory, this phase that I found, the U1 gate, there's a Higgs field that's condensed. The Higgs field is charge 2. The 2 came from insisting that these factors were exactly integers. And then you're moving exactly one lattice space into unity and so on. But so by doing it this way, you made a choice. You called one link a gauge field, the other link a gauge field, and the third link became a Higgs field. But it could be the other way around. It's actually democratic. None of them is allowed. Any of them is perfectly reasonable interpretation. if you insist on such an interpretation. So the correct interpretation, really, which is completely democratic, is that we have a Z2 gauge theory, that the gauge U1 gauge field is gone, and you only have to worry about a gauge field that's 0 or pi. Everything else is massive. And so you end up with a phase which has an emergent Z2 gauge field.
Would we have derived that directly from?
Yeah.
Okay.
Derived it directly from what? Well,
Did you say that?
Yeah, and actually that's a good point. I should have made that. So how could we have done this without all this work? I'm just trying to motivate it. You had a saddle point. You can look for gauge transformation that leave the saddle point invariant. Use spatially uniform gauge transformations. And then you find for the triangle lattice, there's only a Z2 gauge transformation that leaves the saddle point invariant, even up to gauge transformation. It's exactly the same saddle point. That's for a spatially uniform. Whereas for the other one, there's a staggered gauge transformation on the square lattice. However, that argument is, for the Z2 case, that's a little fishy because the Z2 gauge field is massive anyway. So it doesn't really tell you, so the invariant statement that there's a Z2 gauge field has to do with the fact that there are magnetic charges which carry Z2 magnetic charge. That's what we'll go to cover next time. Yes.
You could probably argue that on torus.
Yes.
Like some kind of Z2 gauge.
Absolutely. Yes. That's what we're going to do, in fact, next time. Right. So you do have to make kind of a topological argument to say it's Z2 gauge field. Yeah.
You have different such states depending on which choice you make here?
No,
Or are they,
no.
so they're the same state?
They're the same state, but different. This is just your choice to call one of them a gauge field and the other one a Higgs field. You could do it any other way. They're not three different states. It's the three different descriptions or continuum limits. Or let me put it this way. When you're doing the integral, you're the integral over K over all over the Brillouin zone. Okay. So here's your Brillouin zone. And you have fluctuations everywhere. But if you're near this momentum here, you choose this picture. You need these momentum here to the other one, and there's another momentum here to the third one. You really have to, and they're all connected. They're not like separate degrees of freedom. It's just a question of how you think of it. Now, if you're in a limit where this Higgs field is a very small mass, then you're right. Then there'll be three different Higgs fields near these points.
But then will there be three different vacua?
No. These are the fluctuations about in some continuum limit near some quantum critical points where the Higgs field are becoming very weak.
In that case, there would be three different gauge fields and three different Higgs fields.
Yeah, so it'll depend. That structure will depend on the next phase that you're going into when the Higgs fields gap out. Yeah, when the Higgs fields are no longer condensed.
But from your description, you made a choice with all this.
Yeah, so I justify the choice because I'm looking at a different lattice. So only for that lattice is it strictly justified to do this, where these bonds are weaker than those bonds, say. So we just had a slightly distorted square lattice. Then you just preserve the same gauge fields you had on the square lattice, but the diagonal bond becomes a Higgs field. But if you have a triangle lattice to begin with, really the continuum description is not useful. You should really sum over the whole momentum. Yeah, there is no clean. There would be a continuum description if the Higgs field, for some reason the Higgs field became very light. And you're about to restore the some Coulomb phase of some type. And then maybe you'll get three different things.
Hello.
Yes.
Yeah. So you said that. Yeah. So this G2 nature of this gauge field is emergent on triangular lattice. So
yes.
Is it related to geometry of the lattice? I mean, if I have taken another non-bipartite lattice and did the calculation.
I think that.
Yeah.
Yes, the answer is that it's related to the geometry of the QIJ. I mean, you could imagine on a triangle lattice for some strange Hamiltonian. Suppose you had a triangle lattice like this. Sorry, I should draw a nice triangle lattice. You could imagine a situation. Let me just draw one triangle, or two. All right, so here's my triangle lattice. And I minimize over the set of QIJ. And I find that the energy of the Qij is such that this Q1 is not equal to 0, this Q2 is not equal to 0, but the Q3 is equal to 0. There could be a situation where that's the global minimum of energy, some set of interaction. So now this global minimum has broken a lattice symmetry. It's what we call a nematic state. It doesn't have 60-degree rotations, but it's still a spin liquid, and it'll have a photon. It'll be U1 gauge theory with a photon. We'll describe the low energy fluctuations about this vacuum, where there's a kind of a boring traditional symmetry that's also been broken. But the Hamiltonian has the full symmetry of the square lattice. So it's a statement not of the geometry of the lattice, but the geometry of the Qij in your saddle point.
Okay, thanks.
And even on the square lattice, you could have second neighbor interactions. In fact, this is the case we looked at first. This one would have these interactions. And if those Qs are non-zero, then you have a Z2 spin liquid. If these Qs are 0, then you have a U1 spin liquid. And that's what was in our papers in the late 80s, early 90s. So depending on the geometry of which Qijs are 0 or non-zero, and whether they're bipartite or not, you can tell whether you're realizing a photon phase or a Z2 gauge theory.
Thanks.
And of course, these are the simplest case. There's a way of writing things where you have an SU2 gauge field, or even more. You can get all kinds of possibilities, but this is the very basic structure. Yeah.
I'm still puzzled about the role of the original SU2 global symmetry that you had.
Not much role.
Did I not puzzled much, or it doesn't have much?
It doesn't have much of a role. For everything I've said so far, it has actually no role.
So it could have been an XYZ model.
Yes, everything would still go through. I could even break the spin inversion symmetry and put a magnetic field. All of this would still go through, at least this general structure. You still have the Qijs. They may be different for X bonds, X coupling, Y couplings. And again, you have to look at all of these fluctuations and make sure that whether it's C2.
I guess once it's gapped, that means you could have done any small perturbation of the original grid without changing very much.
Yeah. Right. So there's no symmetry required. Yeah.
Even in the gapless case, when you got a photon in the high dimension, it's
So for example, if you have a magnetic field and you break time reversal, or you break U1 conservation, then you lose this. The spin-ons don't have any and in fact, the E and the M particles become almost the same as it is in the toric core. I mean, I could have done the same analysis to the toric core Hamiltonian, but there I don't need to because you can solve it exactly. Right, and this is, you just need a U1 for this, but there are certain, if you go to, I think the Kagome lattice, and you're trying to classify all possible symmetry fractionalizations. I remember the paper by Yang Chi showing that SU2 was important for certain symmetry fractalization constraints. But we have, for anything I've said so far, it's not important. Okay, good. See you next week.